Why is Metroid so laggy? Many NES games lag, sure. Screens with lots of enemies do tend to slow down. And of course there are Metroid-specific areas that support this. You pass a lot of enemies when you fall down a shaft. Okay. The mini-boss battles have slowdown. Lots of activity here. The life support system on the way to Mother Brain, much of the same. Lots of stuff happening. Of course it slows down. But then there are times when it doesn't make sense, like going through a door. Or walking, running, jogging, whatever. No enemies on this screen and the game stutters. Why is this a problem? Really, why is any of this a problem? The assumption is always because there are too many sprites on the screen. Well, then explain this. A lot goes on under the hood of an NES game. How efficiently the CPU time available is utilized each frame is up to the programmer. Metroid was created for the Famicom disk system, and the code wasn't perfect, and then it was ported to a cartridge, and things got a little worse. Let's look into the Metroid game engine and find out why this game has more lag frames than you'd expect. If you are new to this channel, welcome. Things get a bit technical here, but I try not to make the topics too intimidating. With that said, off we go. When the NES PPU draws the graphics to the TV screen, it has to do that at a rate compatible with the television. For an NTSC NES, this is roughly 60 frames per second. That doesn't mean that each video frame is guaranteed to be a new game frame, though. As the video frame is drawn, the CPU works on enemy animation, player input, collision detection, and more to create the next new game frame. When the PPU is done drawing the current video frame, it interrupts the CPU with something called NMI to tell it, hey, I'm between frames. If you have any updates to send, now would be a good time. If the CPU finished the work in time, then it can send graphical changes to be used for the next game frame as part of the work inside this NMI handler time. But what if the CPU didn't finish the next game frame in time? What if the NMI handler period has to execute before the next game frame is prepared? Sometimes the programmer just gives the PPU what the game has so far. Strider does this. Sprites are in the wrong place for a moment in time, but who cares? Let's just plow through it. Mega Man 3 holds back sending a new game frame and repeats the previous frame. At that moment, the game drops to 30 FPS. This isn't just 30 FPS with dropped frames for animation, the physics slow down as well. Whatever is done between frames after the NMI interrupts the CPU in an area of code I called the NMI handler is up to the programmer. The time to execute the code inside the NMI handler may vary a bit. This is very, V-E-R-Y, relevant to Metroid. There are 29,780.5 CPU cycles per frame, or roughly every 262 scan lines, on an NTSC NES. Some of that time is used for gameplay code, like collision detection and so forth. Some of that time is used for the NMI handler, which may spill into the next frame's time. The time to execute all the code in the NMI handler on average is going to be different depending on if Metroid does or does not lag. If it does not lag, all the NMI handler code is executed. If it does lag, some of the NMI handler code is executed while other code is skipped. It's important to note that time is time. Whatever time it takes to execute the NMI handler code, that is time lost for executing gameplay code. Why focus on this for Metroid? The NMI handler times in the cartridge version of Metroid are noticeably longer than the times in the Famicom disk system version. This is one reason why the cartridge version slows down more often than the disk version. Let's build an analysis tool for this and see just how bad it is. We can write scripts and render an overlay with information for the game as it is running. On the right side of the screen near the bottom, there's an area containing two stacked numbers. These illustrate the average number of cycles required for the NMI handler. The top average is for lag frames, some code executed. The bottom average is for when no lag occurred, all NMI handler code executed. Divide either by the total number of cycles per frame and we have a percentage of frame time, which is easier to understand. This is the disk system version. Standard NMI handler frame time here is about 14.4% on average. Lag frames created by walking through this door a few times reduce it to about 11.7% on average. So if lag occurs, we gain back maybe 2.5% of frame time. Let's record these values and check the cartridge version. Roughly 17.3.4% of frame time for a non-lag frame and about 15% for a lag frame. So about the same difference between them, roughly 2.5%. This has nothing to do with collision detection or enemy animation or Samus moving around. This is work between video frames for the different versions of Metroid. And check this out. All of the NMI handler logic for a normal frame on the FDS version is executed in less time than the shortened lag NMI handler on the cartridge version. Time is time. Anything that was a borderline lag frame in the FDS version is now a guaranteed lag frame in the cartridge version. We lost over 3% of frame time with the conversion to cartridge. The question is, why? To the code. If you don't program, that's fine. Let me talk through this a bit. When entering the NMI handler, the game pushes whatever sprites have been set up in RAM to the graphics chip, regardless of if lag occurred or not. This programming method is Strider-esque, or Ghosts and Goblins-esque. Take your pick. If you drop down this vertical shaft and lag frames occur, you can see the door sprites move up the screen for one frame as we fall, but the background tiles do not. And that brings us to the skip check logic for a lag frame. If the NMI handler sees that a lag frame occurred, these subroutines are skipped. Both the FDS version and the cartridge version then run the sound engine subroutine. This is where the discrepancy in execution time occurs. While I didn't reverse the FDS version for comparison, I did scroll through it a bit. The two versions do share many similarities, but there's something worth noting. The Famicom Disk System has its own sound channel, and Metroid made use of it. Because of this, the cartridge version had to either replace or omit FDS audio as part of the conversion. It required the sound code to be altered. Some examples of different sounds include the door bubbles, taking damage, and the screw attack. So obviously, new sounds made for the NES APU alone had to be added to the mix. Is this responsible for the extra cycles in the sound sub? Maybe. Probably. Again, we'd have to reverse the FDS version and compare the code to know the specifics. Heck, we could even make an entire video dedicated to Metroid's sound engine and the cartridge versus FDS version. But in the meantime, let's disable the sound engine for both versions and see what sort of difference it makes. With the sound subroutine call eliminated, the sound no longer works and the NMI handler times are closer now. Using a Game Genie code to disable the sound engine is a teaser of where we go from here. If we want to isolate what slows the game down outside of NMI time, we need to understand the main game loop of Metroid. The best way to do that is to break the game as best we can. A main game loop is essentially a list of what code we want to execute for each frame of gameplay. In an ideal situation, this entire loop manages to execute in less than 1/60th of a second, so it finishes before that interruption from NMI occurs. Metroid manages to do this most of the time, but also has some hitches throughout gameplay. We can isolate which sections of the main game loop are sluggish and drill down into them to find out why. Let me first show you some of the things that happen before we reach the heart of it all. The main loop checks to see if we need to switch banks before continuing. It updates timers, count this, delay that sort of thing. Then it calls Go Main Routine. The main routine handles some housekeeping items like what if they pause the game or unpause the game. It then jumps to Game Engine. First up, Scroll Door. So the door scroll check is called twice before we get to the usual suspects. Due to how it was implemented, calling this routine twice is a cheap way to scroll faster. Does that mean the more you call it, the faster the game scrolls? Let's find out. Let's replace some of the code beneath the scroll door subroutine calls with more scroll door calls. And whoa, that's pretty quick. Sadly, it isn't without some problems. Let's return to normal speed. We already know that door transitions cause lag, and this is a small part of a much larger problem. Underneath the double call to scroll door is the check to see if the player used the NAR password feature. This password will keep Samus's health inside the 30s, max out her gear by setting all flags to true, and keep her missile count at 5. As this is effectively an override for all other health, missile, and gear gain logic in the game, it has to be executed every frame. After that, we call the subroutine Update World. And here is the real heart of the game engine. Most of these subroutines have names that make sense, a few require knowledge of enemy names. I mentioned that we would eventually break a few things in order to understand them, and that time is now. I'll provide some Game Genie codes so you can try it at home, or work or school. Update World first resets the sprite index for building sprites on the NES as it is time to start work on a fresh frame. With that done, let's break some subroutines. First up is Update Enemy Animation. If we disable this, enemies are frozen in place and cannot be seen. They still do damage, unfortunately, so this isn't a free roam exploration code. Next is Update Projectiles. This prevents Samus from using her beam weapon, as one example, and that means you aren't going to get very far in the game. Next is Update Samus. Samus cannot be seen, and the player cannot move her. This would appear to prevent invulnerability frames as well, as a single pass by this enemy takes her health down to 0. Samus is an invisible zombie until we re-enable the code. This also handles damage from lava. Level layout retrieval and placement during movement is also called from this subroutine, and this will haunt us in the future. Next is area-specific code. This subroutine, as well as a couple of other subroutines, are specific to the current ROM bank. As we move from Brinstar to Torian, for example, we switch to a different ROM bank. These banks may contain copies of the same subroutines, such as the ones for the sound engine, or have a subroutine located at the same place in each bank that does different things depending on which bank we are using. For example, if we disable this subroutine while in Torian, the life support system at the end of the game is pretty quiet. You'd think that means you could just waltz right through the chamber here, but it also means we don't execute the area-specific code that handles damage to the life support system. Ah well. Next is the elevator handler. No subroutine means no elevator. Next is Update Statues. There are 2 mini-bosses in the game, Kraid and Ridley. Both of them must be defeated to reach Mother Brain, unless you're a speedrunner. If the mini-bosses haven't been defeated, they are in the down position. Defeating a mini-boss will cause the respective statue to flash. Shooting a flashing statue will cause it to move up. When both statues have been raised, a bridge to the other side will appear. If we disable the subroutine, the statues do not appear in the room. Even if they have been raised already, the bridge will also not appear. Re-enable the subroutine, and everything returns to normal. Next is Enemy Destroyed animation. When you defeat an enemy with the beam weapon, that enemy is vaporized. Disabling this means they just disappear. Note that missile explosion animation is unaffected, as it is handled by our earlier enemy animation sub. Next is Disable, Mellow, Mimu, whatever you want to call these guys, handler. Disable it, and those blue flies will not appear. Next is the Environmental Enemies handler. Disable this one, and area obstacles like the turrets in the life support area for Mother Brain and Torian stop firing. This sub also handles the floor thingies in Norfair as an example of game logic in a different area. Next is Scree Explode handler. These guys drop from the ceiling to the floor, and then rock splinters are sent in all directions. Disable this subroutine, and that feature is removed. Next is Samus Enter Door. This is area specific. If you turn this off, you can't door transition to the next room. Weird things happen when attempting to move left and right. If you re-enable the subroutine, you could probably coax Samus out of hiding off the side of the screen and attempt the door again. Next is Door Bubble Handler, also area specific. Disable this one, and the bubbles are invisible. Your path is still blocked, and the doors cannot be opened. Next is Update Tiles. Turn this off, and breakable tiles don't break. The timers seem to be set, or at least a flag to start the process is set. Re-enable and animation plus collision detection is off, but would seem to fix itself after a bit. Next is collision detection. This one is pretty important. You can't harm enemies with beam, missiles, bombs, or screw attack, and enemies can't harm you. There are a few exceptions. Scree explosions can still do damage to Samus, and Samus can still defeat life support and Mother Brain. Display bar. Disable this subroutine and you disable the HUD. Advanced players may find this useful. Pipe enemy handler. This handles enemies that spawn from pipes. Disable it and they do not appear. Check missile toggle. Handles Samus's ability to switch to missiles. Disable it and you disable switching from beam to missiles and vice versa. Update items. This appears to handle special pickups in a room. If you disable it, collectible power-ups like energy tanks will not appear. Turn it back on to return items to their place. This does not affect enemy drops. Set life support gone. A couple of things happen here. Whenever you defeat one of the life support capsules or Zebatites, the game logs the defeat and integrates it into your generated password. If you leave the room and come back, the game knows to prevent it from spawning. If we disable this subroutine, it will respawn just like any other enemy. The game keeps track of the number of unique items history, items gained, or enemies defeated, and this subroutine also logs the death of Mother Brain. And that finishes our list of subroutines in Update World. After all of those subroutines have been executed during the current frame, unused sprite RAM is cleared out, and we return from Update World. Any timers for defeating a mini-boss or acquiring a suit power-up are handled here. We fall back through the call stack to increment the frame counter and wait for NMI. When the NMI interrupt occurs, we execute stuff we need to do between frames as mentioned previously. After that is done, we start our new frame with the random number subroutine and then jump back to the main loop and do everything over again, starting with the bank switch check just like when we first began this explanation. So there is a skeletal version of Metroid's main game loop through a non-lag frame, an itinerary of code execution that completes before the NMI interrupt occurs. Hopefully. On a lag frame, it is possible that execution only got as far as, say, collision detection before the NMI interrupt hijacked game loop execution. When that happens, NMI work is completed, execution returns to whatever it was doing inside collision detection, finishes, and then proceeds to finish the rest of the loop, followed by wasting time to wait on the next NMI. In this example, we burn 2 frames, or 1/30th of a second, to complete a new game frame. By the way, random number generation in the cartridge version is different from the Famicom Disk System version. The random number generator for the FDS version is built into the BIOS of the FDS. The programmers for Metroid didn't need to write an RNG routine, they could just call one that was available to them. When the game was ported to cartridge, a copy of that routine, or at least something similar, was necessary. What happened was an RNG routine was written to replace the original that doesn't really RNG very well. What sort of consequences are we talking about here? The FDS version would have some functional RNG. An example would be each fireball from Ridley having either a long or short pattern during battle, depending on that RNG. In the cartridge version, this would turn into all fireballs having either the short pattern or all fireballs having the long pattern, depending on the power on state of RAM. If you lucked out and got the long version, welcome to the easiest mini-boss fight in video game history. With our knowledge of subroutine usage in place, it is time to monitor performance via CPU cycles consumed. And yes, you'd better grab a taco. Before I flood you with those subroutine performance numbers, there is something important to explain. How do we keep track of frames and lag paired with reported performance? The emulator maintains its own frame numbers, and we're going to use them as part of our report. Best to think of these numbers as video frame numbers. They are where we've been, the last complete game frame created that is currently rendered to the screen. Where we are, the current video frame. This counter always increments, just like an odometer. And a report on the most recent game frame we completed. I've hidden the details for now so we aren't overwhelmed by numbers. In this example, we see game frame 8789 rendered to the screen. We started and finished work on the next game frame during the current video frame, 8790. Therefore, our report below will show the CPU time breakdown to create the new game frame. We'll name this new game frame 8790, the same number of the video frame on which it was started. This new game frame took 1/60th of a second to complete, no lag. And so, with 8790 completed, we advance one video frame, and that is now the frame rendered to the screen. Oh, and we started and finished the new game frame 8791 within 1/60th of a second. In an ideal situation, this is how it works every single time. A new game frame is created within 1/60th of a second, and then we see it. One video frame equals one game frame. But what if we lag? Let's find out. Each frame in this scene would seem to be fine until we reach video frame 8797. We didn't finish a new game frame on the same video frame we started. The report is the previously completed 8796 that we're seeing rendered right now. Let's advance. Still not finished. 8798 is the same story. Let's advance again. There. We finally finished a new game frame, and it took 3 video frames worth of time, or 1/20th of a second, in order to do it. We finished up during video frame 8799. I used the video frame on which we started to identify a new game frame, so 8797. If we advance, is the next rendered game frame. So again, if we finish on the same frame of video we started, no lag. If it took more than one video frame to finish the new game frame, we had lag. With this frame performance bracket work done, let's talk about performance itself and return to our game loop logic. Alright, here we go. I've assigned a letter to each of these subroutines A through S. That makes it easier to ID them, as we have reduced their label to a single letter. In addition to the individual subs, let's label all activity before the subroutine block starts as pre-sub and track its execution time. This includes everything that happens after the NMI handler completes up until subroutine A is called. In addition, after the subroutines execute, there is time to clear remaining sprites called T, followed by all code up until waiting on NMI, or the finish frame code called U. That is our game loop broken down into lettered sections. Let's add them to our template. Now, each of these subroutines and code areas could take anywhere from 15 to 600 to 7,000 cycles or more. Those values won't really mean much to you unless you're an NES programmer, and they also don't fit well on the screen for this many trackers. So what we're going to do is illustrate them as a percentage of video frame time rounded to the nearest tenth. Each percentage is the cycle count divided by this cycles per frame constant. They take up less space on the screen this way. For any areas that take more than about 10% of video frame time to execute, I've changed the font color to red. As a visual indicator of lag, all subroutines with code executed during a lag frame will have a cyan background. In this example, it took 2 video frames worth of time to create a game frame. Most code completed execution during frame 8800, but T and U had code executed during video frame 8801. Therefore, those 2 numbers have a cyan background. Finally, we have a rounded, full game frame percentage. This is all of our percentages added together, plus the first NMI handler's time for the game frame, the one that kicked it all off. Lag NMI handlers are not included. If you don't know where your eyes should go for all of the stuff on this screen, I'd recommend looking here. This design leaves space for 2 emulator features: a lag counter and the performance tracker. It will graph our FPS performance for recent frames. If you arrived at this video thinking someone was just going to play Metroid along with some commentary about slowdown, well, that's not how we roll here. I hope you grabbed more than one taco. We've built a performance analysis tool specifically for Metroid, and it's time to use it. Despite the usual suspect areas of Metroid, I want to start here, at the beginning of the game. If I take several steps to the left or to the right, the game is going to lag. With the enemies destroyed, let's walk left. This isn't a bug with my script. The Samus handler alone took almost 200% of frame time to complete execution. It took 1/30th of a second just to process update Samus. Why? Would I say that mistakes were made? That's a bit harsh, but I would say that alternative options within the realm of code performance were adopted. Yeah. The update Samus subroutine is responsible for handling many Samus-based things, as well as loading the level whenever she moves and scrolls the screen. We've seen the loading seams in action for several games. Metroid's tile loading sequence for backgrounds would seem to work in columns at a time when scrolling horizontally like many other games. The name table viewer shows us as much. Each new column of tiles appears in red as we continue moving into the next name table. But that is the result of level loading logic, the rate of graphical tile placement into VRAM. At some point, the game had to go find the level data to know which tiles to load where, and that is where Metroid dropped my jaw. When Samus reaches a seam that divides one name table or room from another, Metroid builds the entire destination room in RAM uncompressed. 960 background tile bytes plus 64 palette bytes. Oh, and those bytes are written more than once. But wait a second, 2 screens, where you are and where you're going, and their palette data? That's 2K, that's the entirety of RAM in the NES. Quite right. But that's not the only RAM available to Metroid. Inside the cartridge, there are 2 RAM chips. One is used for character or graphics data loaded from the ROM, and the other is used as work RAM. As a matter of fact, some in-game essentials, such as the number of missiles or which power-ups Samus has, are stored in WRAM inside the cart instead of RAM inside the NES. This is what holds all the tiles and attributes for 2 screens before sending them to VRAM. Of course, for the FDS version, the entire operation flows through RAM anyway, as the system has to load the data and code from disk and put it somewhere, like a RAM cartridge, so it could be accessed. Unless they were to reinvent how Metroid loaded level data when porting the game, placing RAM in the cartridge for extra working space was the way to go. Let's look at the big picture of world building. The entire map of Metroid is stored in WRAM from address 7000 hex to 73FF. If the byte pattern doesn't look familiar, perhaps an overlay will help. Metroid has 5 areas: Brinstar, Norfair, Ridley's Hideout, Kraid's Hideout, and Torian. Each byte here, aside from FF, represents a room ID, and those room IDs are tied to their area. That is to say, room 13 hex in Brinstar has a unique layout versus room 13 hex in Kraid's lair. As for our location and destination, we are moving left in Brinstar from room 9 into room 17 hex. In fact, it isn't difficult to manipulate this world of rooms with a Game Genie code. You know the blue area of Brinstar where you pick up this energy tank? That is room 1B. Let's replace the room to the left of start with room 1B. There you go. Change the room ID and everything falls into place. But let's return to the unmodified game. We know the room ID where we are going, but how is it built? Most NES games we have seen are preset tiles, perhaps 32 by 32 in size. Just line them up. Metroid rooms are constructed on the fly. Each room is made up of various structures. This is one example of a structure. Each structure is built using what we call a macro. A macro is a 2x2 set of tiles. And of course, each tile is an ID that indicates which graphical pattern for the CPU to use to draw to the screen. When we reach this seam between rooms while scrolling, Metroid checks which of the 2 areas of WRAM to use for the new room, checks the room ID for the current area, and uses the room ID to build the room. Each structure is processed. For each structure, each row of macros is processed. For each macro, 4 tiles are written to WRAM. This may include 1 or more unused quadrants. You can see that structures actually overlap one another in this screen's makeup. The bytes from one structure are overwritten later by a different structure. So how long does it take to erase all tiles and palette data with FF, loop through all room structures, process all the macros for each structure, and process and write all the tiles for each macro without actually drawing any of it to the screen? about 5 to 7 business days. And since the structures present will vary from room to room, it takes a different amount of time to build the destination room based on the contents of said room. So if we head in the other direction from the start, we don't have as many structures to load in the next room and therefore don't need as much time to render the room in WRAM. Go either direction and it still takes too much time. The worst part is we only use WRAM for 2 screens worth of structures. For example, if you start in room 09 and move to the left, the game will lag as it renders room 17 hex in WRAM before starting to scroll it onto the screen. If you then stop, turn around, and walk to this point, the game will destroy all the work it just did for room 17 hex in WRAM and use it to hold the structures for room 14 hex. Furthermore, you would think that moving left from the start would at least put you into a room without lag, right? The screen dead ends. Except it doesn't actually dead end, and it lags. Why? Well, this huge wall to the far left is a room. Room 08, an entire room of nothing but blocks. And yes, the game destroys the structure for starting room 09 by writing FF to all blocks first, and then writing wall tiles for the entire room that makes up this wall. Turn around to head back to the starting screen, room 09, and well, now we have to destroy that entire wall room and re-render the first screen. The same is true for vertical shafts as well. One screen after another while moving up or down still results in lag. Just for the record, when you go through a door, the room building subroutines are called from the scroll door subroutine. The Metroid Performance Analyzer showcases this as the processing time is reflected inside the pre-sub percentage rather than updates Samus. Door transitions are essentially cutscenes where the player doesn't have control anyway. A couple of frames of lag here are likely to go unnoticed. The short of it is, one screen for where you are, one screen for where you are going. Whenever you need to scroll past a seam, as indicated by this line, the game will lag. And if that doesn't resonate with you, consider this. Metroid will lag every single time the edge of the screen reaches a room seam in the map. This happens during vertical scrolling and horizontal scrolling. These are guaranteed lag points and do not include processing enemy movement, projectiles, collision detection, or anything of that nature that also requires CPU time. So if you were to team up with Gravity and drop down a vertical shaft, you'll hit a lot of room seams and pass a lot of enemies on the way down. Lag City. We've built an analysis tool and discovered some disappointing performance when it comes to loading map data. This is an interesting case of lag caused not by the number of enemies or animated objects on the screen, but simply the implementation of Metroid's free roaming world. And while this performance may seem disappointing, perhaps it is simply a cost, a compromise, or even something one might consider impressive. Let's back up just a bit. Earlier I mentioned that Metroid was developed for the Famicom disk system and wasn't perfect, but consider the task. 32K of RAM in the RAM cart to hold not just the code, but also the room data after a slow load from disk. There are 45 different room layouts in the Brinstar area alone. 960 tiles per room times 45 rooms is over 43,000 bytes. That doesn't include color information. RAM isn't even enough to hold the tile-to-tile makeup alone of all the rooms, much less any game code. You need some form of level compression. This is true of most games. The world of Metroid is larger than just Brinstar, so it does require loading times from the disk when moving from one area to another. Metroid uses an elevator to move between areas, so the player is already waiting on the elevator cutscene to finish before disk loading is introduced during the ride. That's good design. Plus, the game can scroll horizontally or vertically. When two rooms next to each other scroll across different axes, a door is used to connect them. The door cutscene is used for steering the scrolling and changing scroll direction behind the scenes as the player waits to regain control. So then back to room design. This means for a given room, you may need to load graphics starting from the left, right, top, or bottom, depending on the direction Samus is moving. Add to that the desire for a large number of rooms with unique layouts across the map, and suddenly that level compression requirement is a bit more complex. Using the structure to macro to tile storage method in Metroid to retrieve room layout, Brinstar was compressed from a would-be 43,200 bytes to 3,342 bytes. While the code efficiency for loading and rendering a given room using this compression could be a bit better, perhaps introducing a micro stutter during scrolling was an acceptable cost to create Metroid for the Famicom Disk System in 1986. But what else slows down in Metroid? I want to get into a couple of other things at least, the battle with Ridley and the path to Mother Brain. Is there anything else you would like to see besides these two areas? Leave a comment, and I may include it in part 2. Please like and subscribe for more videos like this one. I also have a Patreon available if you are interested, and thanks for watching.